Log on, tune in, find out. Another good idea from Cambridge.
Before we start, I want to make one announcement, which is that the second talk this afternoon by Marie-France Vigneras will start at 3:30, not at 3:15, so just 15 minutes later than usual. So our first speaker today is Daniel Juteau, who will tell us about cohomology of the minimal nilpotent orbit.
Thanks very much. I will start with explaining the problem. So take G, a simple Lie group over C. We take its Lie algebra G, and G acts on it with a joint action. And inside G, we have a set of nilpotent elements, which I call N, which is called the nilpotent cone, because it's stable by multiplication by scalars. And here there are only finitely many orbits, the nilpotent orbits. And there is a partial order. O is less than O prime, if and only if O is included in the closure of O prime, which is natural order. And now, what does this order look like? So in all types, we have the following orbits. So you have an open orbit in the nilpotent cone, which is a regular nilpotent orbit. So it's a maximal element in this poset. Then you always have the trivial orbit, 0. But then, if you take away the regular nilpotent orbit, then you still have an orbit which is open in the complement. This is called the subregular orbit. So it's maximal amongst the orbits which are not maximal. And on the other side, you have the one which is called the minimal nilpotent orbit, or min, which is minimal among the ones that are not trivial. And then it can be complicated in the middle. It depends on the type, but this occurs in every type. And so we are interested in this one. So maybe I will just give an example when G is SLN. Then the nilpotent orbits are parameterized by partitions because of Jordan reduction. So in the Jordan normal form, you have some blocks, and you can order by the weight, the size of the blocks, and the sizes of the blocks give you a partition. So the regular orbit is the partition N. The subregular, it's n-1, 1. The trivial, it's only 1. And the minimal, it's 1 block to 2, and then only 1. So for SLN, so you can put your 2-2 block before, and then only zeros. But you can also put this one on the top right corner. Then your 2-2 block is here. Okay? And so you see it is the highest root in this case. So actually in general, so say you have chosen positive roots in the root system. So you have the highest root, alpha tilde. So you have the adjoint representation decomposes the carton plus one-dimensional weight spaces for alpha in phi, the root system. G alpha, and say G alpha is the line spanned by E alpha. Then O min is just the orbit of such a highest root vector, so corresponding to the highest root. And now the problem is to compute the cohomology of these varieties with Z coefficients, the usual cohomology, the classical sense. So this is the aim of this talk, but the real aim is motivated by computations with perverse sheaves. So because this is exactly what you need to compute the intersection cohomology complex associated to the nilpotent orbit closure. And actually with whatever coefficients you like Q, Z, or Fp. So this is so the intersection cohomology complex is a complex of sheaves. It is supported on this closure, and this closure is just the orbit itself union 0, because it's a minimal one. And then it is a complex which extends the constant local system on O min. And so the only thing new is the Stoke at 0. And then the cohomology of the minimal orbit, okay, is something, say D is the dimension of O min. Then the cohomology will be in degrees 0 up to 2D minus 1. And now if you look at the IC intersection cohomology complex in the Stoke at 0, this is given. So what you need is the cohomology of O min in degrees 0 up to D minus 1. And there is a special thing with degree D. If we work with Z coefficients. So we'll come back to this. And then actually the other ones can be deduced by Poincaré duality. So it's really the same information. So now, why are these intersection cohomology complexes relevant? So O min bar is a singular variety. You can take the picture of the nilpotent cone of SL2. An example. Then the nilpotent cone, so you have matrices with 0 trace and 0 determinants. So it looks like this. And you have a resolution of singularities by T star P1. And you just construct the null section to a point. And then, so you have the trivial orbit here. And all the rest is a minimal orbit, which is also regular in this case, because there are only 2. So yeah, in general, you will have something singular. And so if you look at ordinary cohomology, you won't have a Poincaré duality between cohomology and cohomology with compact support, as with smooth varieties. But this is when you take the usual cohomology, which is cohomology with coefficients in the constant sheaf, K. But now, if you replace the constant sheaf by this complex of sheaves, then you get something, a Poincaré duality, which works also in the singular case. So this is a geometric motivation for introducing this. But it is also relevant to representation theory, because if you have X singular varieties, say, from representation theory origin, then this intersection cohomology complex has a representation theory relevance. So this is not a theorem, but it is something you can see in the work of Lustig and other people. But there are many applications of this. It's quite amazing. So if you look at the Stokes of these complexes, they solve many problems in representation theory. And so, for example, you have Springer correspondence. So you have the irreducible representations of the Weyl group. And then there is some link with the intersection cohomology complexes of, say, O is a nilpotent orbit. And then you need maybe not the constant local system, but maybe some twisted coefficient system, so a local system. So these nilpotent singularities are relevant for the representations of Weyl groups, but the classical theory is for representations in characteristic 0. And so when I did this computation, so my motivation for this computation. Actually, there are several. So when I did it, just during my thesis, it was to give some evidence that there should be a modular Springer correspondence, so that you have such a link also for representations in characteristic P. So evidence for modular Springer correspondence. At the end of the thesis, I had found this modular Springer correspondence, so I could say it was an illustration for this correspondence. And then, actually, this nilpotent singularity, so the singularity of the singular point in this nilpotent orbit closure also appears in the affine Guaswanian. And the affine Guaswanian has a geometric Satake correspondence. The version of Mirkovich and Vilonen. It is, so you have an equivalence of categories between some category of perversives here and the representations of the dual group over the ring K, so you take coefficients for the perversives in K, but the geometry is over C. And then you get the representations of the dual group over K. And so, again, you get an illustration of how one could use this to compute decomposition numbers geometrically of Vilonen. But okay, one can argue that this is not very interesting because these decomposition numbers are very easy to find directly. So here also you get a decomposition number for the while group, but for ADE types, it's just a natural representation, and you look at the multiplicity of the trivial one. But actually, there is another thing, is that in their paper, Mikovic and Vilonen conjectured that for these intersection cohomology complexes with coefficients in Z, they conjecture that there is no torsion in the Stokes. And actually, in the computations that we will see, there is some torsion. So this gives a counterexample. To a conjecture of Mirkovic and Vilonen about no torsion in intersection cohomology Stokes over Z. And so it might change their view on the long length program. So they might have to do more complicated things to fix this. Okay. So now we'll see how to do this computation. So we'll fix a Borel and a maximal torus. And we have the root system, the corresponding choice of positive roots and simple roots, I call delta. Okay, so I will call that O min was the orbit of a highest weight vector for the adjoint representation. So now we can look at the projectivization of O min inside the projectivization of the nilpotent cone inside P of G. So this is G is a vector space of P of G is a projective space. And this is a closed. So this is a projective variety. And this is closed as well because, so in G, it was the minimal above the trivial one, but in the projectivization, the trivial one is not there anymore. So now it's really the minimal orbit, and so it has to be closed. And so this is a projective variety. And it is a homogeneous space, so it has to be a G mod P for some parabolic P. So now we can see what parabolic it is. So certainly, the Borel B will normalize the line generated by E alpha tilde. And actually, this parabolic subgroups stabilizer in G of this line is a standard parabolic subgroup. And now, what is I? I is a set of simple roots, which are orthogonal to the highest root, where you take some invariant scalar W invariant scalar product. Where is the thing to erase? Yeah. There are many of them. Maybe a note. You can also look at the parabolic subgroup of the while group corresponding to the same I. And so this is a stabilizer in W of the highest root. It's easy to see. And we'll need that fact later. So now I will say a little bit more on the geometry of this O-mean bar. So we'll see there is a resolution of singularities. So we have a line bundle. So I will explain this notation. So if you have H closed subgroup of G and H acts in some V, then G times HV is just the quotient of G times V by H, where H applied to GV is GH minus 1 HV. And the image in the quotient will be denoted, so the equivalence class, I will denote them by a star. This is a classical notation. And so this is a line bundle over G mod Pi. So this is a representation of the torus corresponding to the highest root. It extends to a representation of the levy corresponding to I, Li. And then you can inflate this to Pi. So Pi really acts on this. Then you can consider this bundle and gives you a line bundle over G mod Pi. So if you have G star Z, you send it to the class of G mod Pi. So since you can use elements of Pi here, it's only defined up to Pi, so it's okay. So you have this line bundle. And now the inverse image of 0 is just a null section of this line bundle. So it's isomorphic to G mod Pi. But over O-mean, it is just an isomorphism. So it's just this picture here. So outside of the singular point, it's an isomorphism, and the fiber at the singular point is just this partial flag varieties. So we have this line bundle, and inside we look at what happens if we remove the 0 section. So I remove 0 in each fiber. And this is isomorphic to O-mean. So actually, we could do more generally to compute the cohomology of a C-star bundle on some generalized flag variety, and it would work. But in this particular case, it will have a very pleasant form. So how to do this? So to compute the cohomology of such a thing? Well, the first ingredient is you have a Gisin sequence. So the cohomology of O-mean will fit in an exact sequence where you will know the rest of the terms involved. So I will just call Hn the Hn of G mod Pi. Yeah, I will call just P this Pi with coefficients in Z. And then the given sequence tells you that you have an exact sequence, hn minus 2, hn, then hn of what you want, then hn minus 1, and hn plus 1. Okay, now you can put this in a short exact sequence. So you have a short exact sequence with a co-kernel of this morphism, then what you want, and then the kernel of the other one, and the other. So these are known, these cohomology groups. So this is nice. But still, if you want to compute this, you need to understand this error. But the theory also tells you which error it is. So you have something associated to this line bundle. You take the first Chern class of the line bundle. In general, for Wonk R vector bundle, you will take the top Chern class. And so this is an element of H2 of the G mod P. And these maps are just multiplication by this Chern class. So it increases the degree by 2. So now you have to understand what is the effect of multiplying by a Chern class in the cohomology wing of G mod P. And this is known in the theory which is called Schubert calculus. So the first thing is about the cohomology of G mod P. So it is concentrated in even degrees. And the H2I is free over Z with a basis indexed by some elements of the while loop. So I call this W upper I. So this has a distinguished coset representatives for W mod Wi. So these are elements of minimal length in their coset. So H2I, so for length of W equal to I. So the degree of YW is twice the length of W. Okay, so this is the first thing. And this comes from the Brouillard decomposition. So G mod P is a union of affine spaces parameterized by this Wi, and they are of dimension x of Wi. Now we need the formula to see how to multiply. It is given by a Pierry-Chevalet formula. if you multiply by the Chern class associated to the line bundle corresponding to alpha tilde, but we could take other weights as well. So if you multiply with this basis element, you get a sum of some elements W prime in Wi, which are related to W through a root gamma. So here, gamma is say a positive root, and this means that W prime is S gamma times W. So it's not necessarily a simple reflection, but we ask that we require that the length increases by 1. And we want that W prime is also a distinguished coset representative. And then we get W applied to the weight defining the line bundle, so alpha tilde, and paired with gamma Czech. And this is a coefficient of W y prime. So the length has increased by 1, so the cohomology degree has increased by 2. So it's normal, because C is an element in H2. So actually, this is already completely explicit. So in any given example of any line bundle over any G mod P, you could compute this. So you would have explicitly these maps. And so you could deduce the cohomology of mean. But so here we'll see a little more. So what are the things that occur here? So you have all the orbit of the highest root. So what is that? So alpha tilde is a long root, and the orbit of a long root is all the long roots. So here, the orbit of alpha tilde is the long root, which I will denote by this. And now W upper I, so they're in bijection with the classes modulo Wi. But Wi was a stabilizer of alpha tilde. So this is in bijection with the orbit of alpha tilde, which is phi long. So to some W, I associate W applied to alpha tilde, the thing which appears there. And I want to give a name to the inverse bijection. So I will say to alpha, I associate W sub alpha, which is defined by W alpha applied to alpha tilde is just alpha. So now I want to forget about these Weyl group elements and express everything in terms of roots. So for alpha in phi long, I will write Z alpha for the Weyl W corresponding to alpha. So Y W alpha. So the degree of YW was twice the length of W. But now, if we go to the root side, we have to understand how to find the degree of Z alpha. Okay. So we'll see that later. But what does the Pierre-Chevalet formula become? So we have C times Z beta. So you have a sum from W beta goes to W alpha related by some gamma. So here I would have to write W beta applied to alpha tilde. But by definition, this is just beta. So I get beta gamma check. And here times Z alpha. Now, if we want to understand these coefficients, so actually I would like to replace this. So I want to forget about the Weyl group elements. So I want to replace this by beta linked to alpha through some gamma. So now I have to say what this means. So first, beta must be S gamma of alpha. Okay. But then you need to say something else which corresponds to the length of the Weyl group element increases by 1. So here, actually, what is relevant is the height of the corresponding co-root. So I want that the height of alpha check has decreased by 1. Except in one particular case, unless beta is simple. So beta check is simple as well. Because then if you decrease by 1, you get to 0, and it's not possible. So the next possible level is -1. So in that case, it decreases by 2. So if alpha is simple, alpha is the opposite of simple. Then you have 8 of beta check is 1, and 8 of alpha check is -1. So we say beta is S gamma of alpha. Now let us write down the definition. So it's alpha minus alpha paired with gamma check times gamma. Sorry. Beta. No, it's the contrary, sorry. It's alpha is obtained by beta. It's the next step. Yes, that's better. So this coefficient is how many times you have to remove, to subtract the positive root gamma to get from beta to alpha. Okay? So now let's say, so if there is only one root length, say that all the roots are long. Okay? So let's just choose invariant scalar product so that alpha alpha is 1 for alpha short. And call R the scalar product for alpha long. Then these coefficients are very explicit. So you look at some height, well, height check equal to something, so the height of the co-root. Then you go to the next level, -1. And then you go from beta to alpha, and you use a reflection. So actually, if you are not in this particular case, you will always use a simple reflection. And if gamma is short, then beta gamma check will be equal to R. And if gamma is long, which will be equal to 1. So maybe a remark. Say you have a root alpha, sum for simple roots delta, coefficients n delta times delta. Then it will be long if and only if R divides all the coefficients n delta for delta short. This is an exercise in Bourbaki. And so you see that when you use simple reflection with a short root, then it's normal that it decreases. So you have to remove R times the simple root so that it still satisfies this property. OK. And now, this was the first case. Now, what happens if you have beta simple? So the HH, say, is 1. And you go to alpha minus simple. Let's say minus alpha with alpha simple. So in that case, you have either alpha is beta, and you use S alpha. So S alpha of alpha, let's say S beta. So S beta of beta gives you minus beta. And then the corresponding coefficient. So this means gamma is beta. Then beta gamma ch is 2. You remove 2 times the same root to go from the root to its opposite. Or alpha plus beta is a root. So you have something like this in the Dinkin diagram. And then you use, it's the only case where you use a non-simple reflection. It's S alpha plus beta, which takes you from beta to minus alpha. And in that case, so gamma is alpha plus beta, and the coefficient is just 1. You remove 1 time alpha plus beta to go from here to there. So it's all very explicit, so you can look at the Wong 2 cases. So in type A2, here is your root system. So this is alpha, beta, alpha plus beta. So all roots are long. Now, if you organize them by height, here you don't care about the co-roots thing. You have the highest roots, then the next level is here, then the next level is here. Then you have the opposite of the highest root. So I will make a diagram of the poset. So we start from the highest root. Then you can get to alpha or to beta with a simple reflection. Then if you use S alpha and you apply it to alpha, you get to the opposite. The same for beta. And then I put a double edge to say that we had to remove twice the positive root. And then you also have the things with alpha plus beta. And then again, you have minus alpha minus beta. And so what I say is that each line gives you a basis for the H2i of G mod P. So you have a free abelian group of a Z. And this gives you a basis. indexed by the long roots. So here you have the H0, which is isomorphic to Z, H2 to Z2, H4 to Z2, and the H6 to Z. And then we have this Gysin morphisms, the multiplication by the Chern class, which goes from some H2i to some H2i plus 2. And what this says is that you can describe the matrices explicitly. So whenever you have a simple edge, you put a 1. If there is no edge, you put a 0. And if there is a multiple edge, you put the number, the corresponding number. So here you would get a 1, 1 as a map from Z to Z2. So here you have something which looks like the Cartan matrix. You have 2, 2, 1, 1. So the only bad thing is you don't have the minus signs. And here you would get the transpose of the first one. In general, we'll have the transpose, and this accounts for Poincaré duality. So the fact that you have the Cartan matrix without minus signs is a general fact, but well, so this will correspond to the middle cohomology group. So let me say what the, okay. So another way to express the same information as in the Gysin sequence is to say that there is a spectral sequence with basis G mod P and fiber C star. So this would be like this. So degree 1. And so here you have the cohomology of the fiber C star. And then you have these differentials. And so what this says is that these differentials are given explicitly by these matrices. Then you have to take the co-kernel of this. So this is the E2 page. Then at the E3 page, you would get, so the maps at the beginning are injective. And here you get Z mod 3, the co-kernel of this one is Z mod 3. And then you get, the last ones are surjective, but there is some kernel here. So you don't really need to write with a spectral sequence, but if you are used to this, maybe it's better to visualize it this way. But otherwise, it's just this bunch of short exact sequences. So the cohomology of O-min in this case it goes from 0 to 7. And what you get is Z, 0, Z, 0, Z mod 3, and then Z, 0, Z again. And this is a general picture for the cohomology of the minimal nilpotent orbit in type AN-1. You have Z, 0, Z, 0, Z, then some Z mod N, then Z, 0, Z, 0, Z again. And because in the middle, you have this fake Cartan matrix. So let's see the example of B2. Alpha and beta. So the long roots, there are 4 of them. And there is one in each level. So you start from 2 alpha plus beta, and then you can go to beta using S alpha, but then you remove twice a short root. So it's a double edge. Then you go from beta to minus beta using S beta, so this is a double edge as well. And then you can go from here to here with S alpha, so again it's twice short roots. So here you get exactly the same picture. Well, all the H2i are Z. and all the matrices are multiplication by 2. And so the result is like this. You have 3 times Z mod 2 in the middle. And actually, this is also type C2, and in type Cn, you always have a projective space, and you have a line bundle, which is a O of -2, I believe, and then you always have some Z mod 2 everywhere in the middle. And finally, for G2, so you have 6 long roots. There's also 1 for each level. And then the matrices are given by 1, 1, 3, 2, 3, and 1. Because here, so you move 1 time a long root, then 3 times a short root. Then you go from positive to negative, then 3 times a short root, and 1 time a long root. And so here, the cohomology, you get Z, 0, 0, 0. Z mod 3, Z mod 2, Z mod 3, and then Z again. Okay, so when you go from the simple positive roots to the negative ones, but you only consider the long simple roots. So in type B2, you just take the long simple root, you get something of type A1, and then what you get in the middle with this, what this says here is exactly you have a A-type thing, and this is a Cartan matrix without minus signs. So you will have this in all types. And for G2 as well, you have a A1. And this explains that you have a Z mod 2 in the middle. So I will write the outcome of all this. So remember, D is the dimension of O min. So the first thing, and so the cohomology is between degrees 0 and 2D minus 1. So the middle cohomology group, HD, for min, is, so I need some notation, so let phi prime be the sub-root system generated by the long simple roots. Then what you get here is a co-kernel of a matrix which is almost the Cartan matrix, and you can get rid of this almost. And what you get is a group of the form P mod Q, but for phi prime. And so P means weight lattice. And Q is a root lattice. Okay. And the waist The second part is case by case. So actually, I should say that the torsion-free part was basically already known, so I was really interested in the torsion. And then if you do this thing, so everything is encoded in the poset of long roots with some indications of how many times you subtract some root at each time. But and if you do it case by case, so you find so in the other cohomology groups, you get torsion for the following primes. So for the classical types, so for AN is known, and for BCD you get 2 torsion with, so the example of C2 and CN is similar. Then for the exceptional types, what you get is 2 and 3, 2 and 3, 2, 3, 5. 2 and 3. So it's almost exactly the list of bad primes, but in any case, it's included in bad primes. And now I would like to make an advertisement. Help, welcome, collaborator wanted. So I would like to have an a priori proof of this fact. And Michel Brillon suggested to use the following structure. So in this computation, we use the multiplication by Chern class, which is like a weighting operator, E operator. But actually, there is a joint, like a F operators. In the other ways, we have a representation of SL2. And maybe one can use this structure to give some general proof of this. And actually, the bad primes are not very far because we are dealing with the highest root, and the bad primes are the characterization with the coefficients of the highest root. So it should be possible to get this. And maybe it would be interesting because, so as I said, to get the intersection cohomology complex over Z, you need to truncate. So you will only get this. So this middle one, I said it has a special role. So actually, it's exactly what controls the decomposition number associated to this singularity in representation theory. So for the Weil group, so you will reduce this modulo P and look at the dimension. So for the Weil group, this gives you for the natural representation. And for the reductive group, you have the weights 0 and the highest short root. So this one, we understand what it means. But in the others, so there is some torsion in Mirkovich-Vilonen conjectures that was known. So we can still hope that the conjecture is true for good primes. If you look at ZP coefficients with P good. But it seems not easy to, it doesn't seem to be an easy conjecture, but it would be nice to have a general proof for this case, which is a particular case, at least to see the good primes show up naturally. And yeah, I think I said what I wanted to say, so thank you.
In the PSB, you say this, you know, the
Yeah.
divided.
Yes.
So you can have a power of 2 and power of 3.
So the only case where there is a power is in type F4 and there is a Z mod 4.
It's the only case.
Yes.
Otherwise,
Always some Z mod P. And also it's never, if either torsion free or torsion, it's never the two at the same time.
Any other
questions?
Was the Markovic villain projected just for this particular field?
It's for all intersection cohomology complexes on the affine Basse-Normandie.
Have you, is there something similar that works for some larger nilpotent orbits?
The other general thing that I couldn't understand is another easy case. So it's between the regular orbit and the subregular orbit. Because then you have a simple surface singularity. And then you also get some P mod Q for some Wood system. And in ADE types is the one you started with. And then you can even control some non-trivial local systems on the subregular class.
Okay. And do you have some similar sort of theorem about torsion in that case?
Well, you also have a critical thing here, but there is not room for more things, actually.
Oh, okay.
Because it's of codimension 2.
Mm.
So,
Okay. Any other questions? So if not, let's thank the speaker again.